What's up, YouTubers? So for today's video, we're going to do a continuation of my short video series on MIG related issues. So that's gas shielded short arc short circuit MIG process. Today we're going to be tackling in specific welding thick steel with the short arc MIG process. And I think this video is going to be eye-opening to some of you, because there's going to be a lot of issues we're facing with this. So with that said, let's get into it. So what I have here is 3/8 thick plate. So pretty heavy thick plate. I did clean the mill scale off of it. And what we're going to do is we're going to short arc MIG weld this in a fillet weld position. And the purpose of that is so I can demonstrate the limitations of a process for you guys so that you become more educated on what to do and what not to do. And this kind of coincides with the video series I've been doing with shorter videos with MIG to kind of get you guys up to speed fast on, you know, the limitations and just instill knowledge that'll make you a better welder and hopefully not cause you to make mistakes that lead to failure. Now, I know that a lot of us will never probably weld a lot of 3/8 plate in a home shop, and you might think this is irrelevant to your situation, but one of the things you got to remember is that what's to say a buddy or a friend wouldn't have you try and weld up something on a tractor or an implement or who knows what. Like when you become a welder or you're known that you can weld, it's very common for people to bring projects over to you, and who knows, at some point you're going to be exposed to thicker plate or some kind of bigger steel. I don't know, not necessarily casting, but you get the idea, like something thick, heavy steel. And if you don't know what you're doing, you can make a weld that looks good, but it's terrible internally, like it has no penetration. So that's kind of what we're going to tackle today. Now let me get into a little bit of the book smarts of this, and then we'll actually do a weld and then break it. So I'll try and keep the book smarts to a minimum here. What we have here, because it's so thick, we can run into issues with the short arc MIG of getting penetration in the root. And it really comes down to the simple fact that this plate, especially in a fillet weld, has so much heat sink to it that it quenches that molten puddle very fast, which is going to limit the penetration. Basically, the penetration and the weld itself will bridge from this piece to here, and it won't melt that root together. And that's very common with gas shielded MIG, so short arc MIG, and that's why processes like spray arc exist, which is very high settings. Now, my particular welder, even though it's a 200 amp welder, cannot spray arc. It does not have enough voltage. So spray arc is used on thick plate like this because it doesn't have that issue of poor penetration. Flux core wire in a 200 amp MIG welder will actually be able to penetrate this thick of steel. So if you have a 200 amp MIG welder, you're going to want to be using flux core wire to weld on this. Now, you could technically preheat these plates to gain some penetration. The issue I have recommending that is that, well, to what degree of a preheat? Well, if you're off by 30 degrees on your preheat, you may go from some penetration to zero, and then you have a weak weld, mechanically speaking. So unless you're willing to spend the time to make sure what you're welding is exactly up to temp or a little bit over, you're wasting your time with the preheat because you're basically guessing. And that's really the point of this, is that you don't want to guess when it comes to making strong welds. Like, yeah, it'll look a certain way and you think it might be all right, but guess what? You know, if you don't have any root penetration on a plate this thick, you're in trouble. I mean, there's no question about it. So with that said, let's set this up. I'll tack it and then I will weld it. So this welder actually does have settings for 3/8 thick plate. Now, I'll be honest with you, my generator that I'm running this on does not have the output necessary to weld at these values. The interesting thing is that I've actually metered this welder at somewhere around here, and it was outputting probably 180, 190 amps at this. So I can only imagine what the output would be here. I think it would actually exceed what it's rated for. Now, the duty cycle here, it goes without saying, is probably 1%. So you're not going to be doing any kind of production at these values for this thick a plate. So we're actually going to use values closer to like between these two for 3/16 and 1/4 inch plate. That's what we're going to stick with. I know my generator can supply enough power for that, and that's also very typical for these power output levels of if you have a 180 amp MIG welder, or if you have maybe a little bit less than that, so in that ballpark. So this is going to be an accurate representation of what would happen if you tried to weld 3/8 plate with a 180 amp or less MIG welder. And even worse, if you have a 140 amp MIG welder, you really have no business attempting to weld 3/8 plate with a gas shielded short arc. It just isn't going to penetrate at all. It's going to be like a bead of caulk on the plate. But with that said, I'll set up the welder for somewhere. We'll run, I don't know, we'll do 310 and 21. So I got the plates here. Let me tack them up and we will weld them. Now I am going to do straight in for half of this, and then I'm going to do a circle E movement for the other half. So if we look there, if I can get this to focus, our bead doesn't look too bad. Get the shadow out of it there, sorry about that. Our bead doesn't look like it's not wetted out. It doesn't look too bad. So what we're going to do now is we're going to do a cut and etch on both sides of this, and then we're going to bend it and break it and see what happens. Well, I got it cut thanks to the Diablo carbide blade. Pretty amazing that a cordless Sawzall can cut through stuff like this. I mean, don't get me wrong, it took a while, but I did it for you guys. So, well, with that said, let's look at the cut and etch. So we can see that there's virtually no root penetration. The lower plate, it bit in a little bit, but keep in mind that this is 3/8 plate. You're talking about, you know, not even a 32nd or a 64th of an inch on any of this. I mean, it's nothing. Now, the left side of that upright plate, that was sheared, so you can see how it kind of has a curve towards the right. Well, there was a slight curve towards the left on the right side of that upright plate, so that weld is literally just sitting right on there. The root itself, there's a clear, distinct line that goes all the way to the edge of the plate, the upright plate, and we'll see when we brake test this later how poor the penetration truly is. And this is a weak weld. I mean, had we had any kind of penetration in there, it would be better. So let's look at the opposite side to what we're looking at here. So this is the exact opposite side. Now there was a little bit of material removed from the saw blade, and then when I ground it flat, so it's a little bit, maybe like 1/8 of an inch or so, 3.2 millimeter away. Same run straight in weld though. And when you look at that little line where the plate on the upright meets the bottom and how it goes all the way past. So there, again, no root fusion, no penetration here. And it looks better than it really is, I guess, because this is such thick plate, but there's nothing. It's just sitting on there. Here's the same weld we just saw at a different angle. And look at that line underneath there, like zero root fusion and basically no penetration. All right, let's look at the other side where I did a oscillation, or a circle E, I mean. So on this, where I did the circle E, you can see even less penetration on the root than the other ones. You can see where the curve of the bottom plate, since it wasn't milled flat, so the bottom of the upright plate, how it comes up and it never fused any of that. And that's actually beyond the edge of that plate. And we'll see it definitely in the brake test where you're going to see a clean edge on that. Not good. So we do have more penetration in the bottom plate and a little bit more in the top plate doing the circle movement, but it didn't do anything for the root. It did flatten the weld out a little bit, which I like that, and we definitely deposited more metal. It's a bigger weld than going straight in as a stringer bead. but I don't like this either. It's still not any good. Now here a little bit closer of a picture, you can see that dot where zero fusion. And if you can imagine that plate is slightly curved on that upright plate towards the right, you can see that, you know, the intersection of that root, no fusion. Like I said though, it does have more fusion in the bottom plate, which is good, and more in the upright plate, which is also good, but strength-wise, other than the weld being bigger, it's not necessarily that much stronger than the previous weld. So let's move on. So pretty interesting results, isn't it? I'll be honest, it was pretty much what I expected, and that's because the short arc MIG process really isn't known for great penetration. It doesn't surprise me either based on my previous video that doing the circle eave movement limited the root penetration even more, although it did bite more into the sides, which is good. You can tell that this weld is slightly wider than the single stringer. Now these aren't a weave or anything, but it is a little bit wider. And this really is a great test that shows what the limitations of the short arc MIG process really are. Now, I'll be honest, if I had a bigger generator where I could run this welder full bore maxed out, it may have slightly more penetration on this thick of metal. But one of the things you guys got to understand is that wire, when you're welding with the MIG process, depositing more metal, meaning that the weld is thicker from the center of the root out, so the throat depth as it's called, the more metal you put down means more from the root out. It doesn't necessarily mean from the root in, so penetration. And I have a feeling that higher values for wire feed, that it's not really going to have more penetration. It will just have a bigger weld. And just based on what I'm seeing here, this weld that was just run straight in is appropriate in size for 1/4 inch material. It is not appropriate for 3/8, so for this material I would have to do 2 more passes on this to get it to the proper height for this thick of material. So that 3/8 setting is kind of in theory to 1 pass 3/8, but you really wouldn't want to do that without, you know, I guess using flux core or something else that has far more penetration on this 3/8 plate. And, you know, realistically, if you ran 2 more passes on this, would it be stronger? Well, it would to a certain extent, mechanically speaking. However, that lack of root fusion, depending on what this is, could lead to a failure. With that said, let's talk a little bit about the oscillation versus a straight end. So I know a lot of guys love doing the stack of dimes look, and I'm not really that good at it because if I want a stack of dimes, I'll just either use 60-11, 60-10 or TIG weld it, but I did a mediocre job at this, and if you notice here, it's fairly flat. The height difference between the peak and the valley isn't that significant. When you see guys in motorsports welding and just a lot of MIG welders in general, they have huge discrepancies or differences in the height of their dimes to make them more pronounced. Well, guess what? When you do that, that means your settings are cold enough to get that look. Well, guess what's going to happen? You're going to have 0 root fusion and very weak welds. So I was successful in having basically 0 to a little bit of fusion on this right here. Imagine it would be negative. It would literally bridge over the root, and you don't want that. So if you're going to do like the circle E movement, I would recommend, well, 1, don't do it on thick plate like this, and 2, be hot enough to where when you're doing that movement that, you know, you produce a weld closer to what this is and not such a distinct cold stack of dimes, because that's weak. You don't want that. Also, if you look at the profile of this weld, it's actually not like, it doesn't have poor fusion on the toes. It's fairly, you know, it's a little bit convex, which is fine. It's not, or concave. There's no undercut. There's no real lack of fusion per se, especially like you look at this. From everything on the outside, it doesn't look that bad. And if you saw this on something you own, you would be like, oh, okay, that's a decent looking weld, yet internally it's garbage. And that's why it's so important for you guys to actually test what you're doing occasionally to get an idea. Because in this case, depending on what it is you're making, you could have a failure. And the best example I can give of something like this is a buddy of mine had a tow truck, and he tried to repair a crack in the boom himself, and he used a short arc MIG process, and his machine, he could only get up to, I think, 140 amps on it because he only had 110, 120 outlet. Well, anyways, he had ground the boom, which the boom was 1/2-inch thick steel. It was even thicker than this. And let's say this is the top of the boom. It had a crack like right here, okay? He had ground it out somewhat, and then MIG welded over it like 3, 4, 5 passes, and it had a bead, a cap on here, and it looked good. Like visibly, it looked good. But it kept cracking right through all of his welds, and then he'd grind it out and then do it again. And then finally he came to me and he says, dude, what the hell am I doing wrong? I can't keep this from cracking. And I said, well, let me look at it. And then when I realized what he was doing was he was short arc MIG welding it. And yeah, he ground it out almost to a feathered edge on the bottom, but the problem is that internal, we're down in here, that weld was just bridging the metal, and it left an unreinforced area for a crack to reoccur on that. So what I ended up doing with him is we V-beveled it all the way out. I TIG rooted it and did a fill pass on it with TIG just so I knew it was 100%, and then capped it end to end. And it was a pretty wide section, like maybe 6 by 6 or 8, probably 8 by 8, 1/2-inch thick square tube, and capped it all the way out with 7018, and it never cracked again. So this, you know, you got to understand the limits of what you're using your welder for. And 1/2-inch, 3/8 plate, you should really be telling yourself stick or TIG or flux core wire dual shield or spray arc. Stay away from short arc MIG on this thick of material. So we're going to do a fillet weld break test. Now this is a small section of it, and we're going to be breaking it to the face. Now normally it's going to take a lot more force to break it away from the face, and that's because of leverage. When you break it towards the face, we're using the actual weld as essentially a pivot point, and we're increasing our leverage. When you do it this way, we have to tear the whole weld either off the plate or through the middle of it, which takes a lot more force than using the weld itself to aid us. But we still will get some useful information from doing this. That took, I would say, somewhere on the order of, I don't know, maybe about 50, we'll call it about 65 pounds there. And let's take a look. I didn't break it all the way on purpose. Let's take a look at it. As you notice, this plate edge, the original plate edge, zero fusion there. It's a 90-degree angle. And you can see it tore up through the weld. But even this, if I were to bend it back, like there's basically no fusion really anywhere. And this even right here is suspect. Like I have a feeling that would just peel off as well. Considering the force it took to bend this off, I mean, this is definitely a weak weld. Had we welded the other side of it, then obviously it's going to be a lot stronger, but you don't want these indications in your weld at all. So what I'll do now is I'm going to break it the rest of the way and we'll look at it again. When you look at this, you see how the original line of the plate still exists? You don't want to see that. When you do a break test like this, you want to see kind of like a squiggly line. I mean, you're going to get a line, no doubt, but you don't want to see that original edge completely untouched. I mean, right here you can see this didn't even fuse in there, that didn't fuse in there. So all of this is no good. Trash. Don't want it. So what did we learn today? Well, we learned that the short arc MIG process probably shouldn't be used on 3/8 plate, especially if you have limited output of your welder or limited power to power your welder, such as in my case. And we learned that you can make very acceptable looking welds that do not perform that good. Now, keep in mind, had I stick welded this or flux core wire welded this, even for these little coupon parts that I broke, which you saw one of them, the other one I didn't film, had that been welded with more penetration, it would have taken significantly more strength to bend it even towards the face of the weld. And that directly coincides to like real world performance. No, it's not a perfect indicator, but you know, again, if your weld is going to experience a lot of stress, we want root penetration, especially on steel this thick. And anytime you see failed welds on thick steel, 9 times out of 10, someone short arc MIG'd it. And that's in my experience. And that's due to, again, the poor penetration of it. And there's just no way to tell what's inside. I'll have to do a video comparing in the future, like TIG, stick, and MIG, where we weld 3/8 plate. And you're not going to see like poor penetration with TIG and stick so much as with MIG. So it's just something to keep in mind. And this isn't a bashing MIG welding process, because wire welders can weld this thick. It's just you should be using flux core dual shield wire, or if your machine has enough power, you should be spray arcing this, and then you don't have any question. And that's really what this lesson comes down to, is that we all have opinions on what works and what we should do. But one of the things you're going to learn as you become better at welding and just stuff in general, there's certain things you do because you know it works and it's reliable. And the best example I can give you of that doesn't relate to welding is that if you talk with guys that do a lot of painting, like they're painting contractors, they have a particular set of paint that they work with. And when you contract them to do a job, they take the paint that they want in the color you pick, and they roll it or brush it, whatever it is, spray it on your wall. Anytime that you try and force them to use a product that they don't use or they don't like, they a lot of the times either won't do the job or won't warranty anything. And that's simply because they know what works. It's predictable. When you start adding variables and stuff, the outcome is rarely good in my experience. And in the case of paint, like you may have an adherence issue, it may take twice as many coats, it may not look as good, etc. Well, with welding, by adding variables of, oh, whatever, it'll short arc MIG this thick steel, it doesn't matter, it looks good. Well, yeah, until you actually need your weld to hold something and it fails. Like, I've seen pictures of failed D-rings on shipping containers that were welded with the short arc MIG process, where the welds looked perfect and they just pulled right off the container because nothing stuck, because they were welding over mill scale. And keep in mind too, guys, I welded on clean 3/8. You can imagine that had this had mill scale on it, oh man, there would have been zero penetration, and I probably could have broke that with 20 pounds of force. And that's something I probably should have done in this to demonstrate it, and guess what? I didn't, but it is what it is. With that said, I hope you guys learned something and you can make better decisions on what to use for welding thick steel, and thanks for sticking around. Until next time.